Hello, physics students. In this session, we're going to take a look at example problem number 4. We'll work through that problem all together. There we go. So we have a pendulum pulled back. We're going to set up the wave equation to be able to take a look at this situation. So in problem number 4, we have a 30-centimeter pendulum pulled back at an angle 40 degrees from the vertical. Where is the pendulum degrees from the vertical when it reaches a speed of 0.8 meters per second for the first time? How much time passes for it to reach this point? So for us to be able to solve this problem, we want to develop the wave equation that would be necessary to analyze this motion. So we are going to take a look at that, right? So in our wave equation, we have the position of the object as a function of time is equal to the amplitude cosine angular frequency times time plus the phase constant. So what we want to do first is develop a variable or a value for each one of those variables that are in the wave equation. So if we draw ourselves a picture of the pendulum hanging, the information given, we're going to pull this pendulum back by an angle of 40 degrees. So we know that to be the case, right? So that, remember that the pendulum is going to swing back and forth. And as it swings, if we project down onto the axes, like I did with the demonstration with the salt, we would be starting at this position. This is our equilibrium position. And the pendulum, as it swings back and forth from its highest point to the low point, back up to the high point in the other direction, we're going to get a wave that gets created like this, right? As it goes back and forth and back and forth. So this distance right here represents our amplitude A. So the first thing we can determine based on the geometry is that distance to give us the A for the amplitude. So looking at that triangle, with the hypotenuse of the triangle being the length of the pendulum as 30 centimeters, we can determine A by using the sine function. The sine of the angle theta is going to be our amplitude divided by the hypotenuse, or L, of the triangle. So we know theta to be 40 degrees. So solving for A, that's going to be L sine theta. A is going to be our length of 30 centimeters times the sine of 40 degrees. So the first value that we can determine is the amplitude of our wave to be 19.28 centimeters. Next, what else we could use here is we're looking at omega, right? So that gives us our amplitude. Omega is 2 pi over the period. So another variable we should be able to solve for is the period of the pendulum. Using that, we will then solve for the angular frequency. So the period of a pendulum is 2 pi square root of L over G. And so the period of this pendulum is going to be 2 pi square root of the length, which is going to be 30 centimeters, but we're going to write that as meters, 0.3 meters divided by 9.81 meters per second squared. Plugging in those numbers and solving for t, the period, we get 1.099 seconds to be the period. So we can use that as the period. I'm going to go ahead and write our omega like this and not solve for an omega. Instead, we're going to keep that and rewrite our wave equation with that in it. The final variable is the phase constant. So the phase constant is where are you at the beginning? So it looks like on our wave, if I go back to my wave diagram, I actually start at the A and I head towards 0, right? So I start at my maximum and I head towards 0. If you go back to the image of your unit circle, right? So I'm starting here at the 1 value and heading towards 0, which means my phase constant should be 0. So in this case, my phase constant being 0, because I start at the amplitude and head towards 0. So again, if we think of our wave now that's going to be created, I started at A and I headed down towards 0, right? This is your negative A. So I'm starting right here. So I could use the formula that our phase constant is equal to the inverse sine of where are you when t is equal to 0 all over A. So that's our equation for a phase constant. Plugging in that we begin at A, we have A divided by A for the inverse cosine of 1, which then is 0 degrees, right? Or 0 radians, because we would be in radians. So now I have lots of variables to be able to be used in my wave equation. I have the period, I have the amplitude, and I have the phase constant. So now I'll be able to just plug in my information of what I was given and what I know and what I want to know to solve for this equation. So the equation for position is equal to A cosine omega t plus your phase constant. The equation for velocity is equal to negative A omega sine omega t plus phase constant. The reason I also want to look at the velocity equation is because the information that I know is that the length of the pendulum is 30 centimeters. The angle in which I pull it back is 40 degrees. And I was given the velocity. I want to know the time it takes to reach a velocity of 0.8 meters per second. So again, going back to the problem, right? I want to know where is the pendulum, so the position when the velocity is 0.8 and how much time passes for this point. So in order to solve for this, I'm going to actually have to use the velocity equation first because that's the information that I'm given to solve for the time and then use the time to solve for that position of where I am at. So plugging in all the values, I would say that my velocity, v of t, is equal to negative the amplitude of 0.1928 meters times my omega, which is 2 pi over the period of 1.099 seconds, sine of omega t, so that's going to be again 2 pi all over 1.099 seconds plus 0. And the t right here. So that's our unknown that we're going to want to have for the t. So on the left side, we do know that velocity to be 0.8 seconds, right? Equals that whole quantity. So plugging all that in, I guess I could rearrange the equation, right? Is the better choice. So I guess algebraically, really what we want to do, I apologize. So better problem solving skills would be to rearrange our equation to say v of t divided by negative a omega is equal to the sine of omega t plus 0. So we'll leave that 0 out. So I'm going to take the inverse sine of both sides. V of t all over negative a omega equals omega t. Dividing both sides now by omega again will get us our t. So plugging in our values. The one thing I want to point out that we didn't take a look at is this is a velocity, right, which is a vector quantity. So if I come up here, I'm going to take things going to the right to be positive, left negative. So I am going to write that as a negative velocity because it is going to be going to the left compared to the height of my amplitude. So when I come down here, when I put in my values to solve for t, I'm going to get the inverse sine of negative 0.8 meters per second divided by negative, the amplitude, 0.1928 meters times the omega, which is 2 pi divided by 1.099 seconds. After taking that inverse sine, you're then also going to divide by your omega again, which is going to be 2 pi divided by 1.009 seconds. That's going to be your t. Now, I suggest you plug that into your calculator at different stages. Once you solve for all of that, you should get your time to be 0.142 seconds. That's how much time passes by for the pendulum to reach that velocity. Since I then have the time, I can find the position of where it would be when that amount of time passes by. So now I'm going to use that time in my position equation. So again, the question is how much time goes by before it reaches that speed, right? So now we're at 0.142 seconds. One period is almost 1.1 second. So we're nowhere near even 1/4 of a period, right? 1/4 of a period would be this part. So we're somewhere in this first part right here, thinking about the time that is going by. So now I'm going to use that time in our position equation to solve for where is the pendulum at that time. Going back to our equation of A cosine omega t plus phase constant. That phase constant is 0, so I can eliminate that. So my position, x of t, is equal to A cosine omega t. So we're solving for that position. So my amplitude remains the same of 0.1928 meters. Cosine of 2 pi divided by 1.099 seconds times 0.142 seconds. Remember that this has to be in radians. So you are in radian mode here. You also should be in radian mode over here when you take the inverse sine. So make sure your calculator is in radian mode. So I apologize for just now picking up on that. Make sure that you had your calculator in the right mode as you are solving for these variables. Up here, we would want that to be in degree mode because we did use the angle of 40 degrees, whereas in the wave equation, we are using radian mode. So plugging in our numbers, we get our position x of t to be 0.133 meters. Now, the question was, what is the angle away from the vertical? So now we want to go back and redraw our pendulum to say, okay, we were here. We pulled it back by 40 degrees right here. That's 40 degrees. That distance here was our amplitude, and that was our 19.28 centimeters. Now we are at a distance of, green, huh? Now we're at a distance, we came down a little bit, right? And this distance is what we just found to be 13.3 centimeters. So the question is, what is that new angle there? So if I go off to the side and redraw that triangle, it is still true that the hypotenuse of the triangle is still the length of the pendulum of 30 centimeters. So we're looking for this angle theta. We know this side to be 13.3 centimeters. So I have the hypotenuse and I have the opposite side. The O and the H go with so. So again, we're going to say that the sine of the angle theta is equal to opposite 13.3 centimeters divided by hypotenuse of 30 centimeters. So my theta is going to be the inverse sine of 13.3 centimeters divided by 30 centimeters. For this, we can go back to our degree mode. We'll be in degrees, so we get our answer in degrees. You can keep it in radian, but that would just give you your answer in radians. We're going to go with degrees, and I get 26.32 degrees. Quite a long problem, but only long because you had to find all of those variables. Awesome problem to incorporate the wave equation, right? So we had to use the geometry of the pendulum swinging to find the different variables that we need in amplitude. We had to use the period equation for the pendulum to find the period. Using that, we could find the angular velocity. We had to think about the wave that was created by the setup of the problem to find the phase constant of 0. Plugging those values in, we were able to use the wave equation for position and velocity to find the variables being looked for. A problem to be proud of.